All right, so Newton-Raphson method, proof, and whatever. So I think Newton actually published this method after Raphson back in the 1700s and such, or 1600s. Um, but either way, we're going to be using, I guess, not Newton's notation necessarily, but um, it simply coined the Newton's method, at least in my textbook. So so what is the Newton-Raphson method? So the Newton-Raphson method is essentially a way to calculate roots. So for example, like if you had a function like 4.86 x cubed plus x squared plus 40, you would wonder um, how you would be able to find what makes f of x 0. And the intuition is that this was back in the day, so there was no way to just use your calculator and click the root button or the x-intercept button on your calculator. So how do you do so? Well, this is what the Newton-Raphson method is for, and let's go over the logic here. So back in chapter 2.8, you learned about linearization, and linearization is essentially a way to get an estimated function made by simply the derivative at a point and the differential at a point, and also the height of the estimated guess. So if that doesn't make sense to you, I'll just give you the formula. And I'm going to also give you the derivations simply because I don't think that understanding calculus without the derivations is logical. So we can rewrite this. Well, let's start from first principles, where the derivative as well, actually, let's not use that. Let's use the slope formula. So it's going to be f of a minus, or f of x minus f of a is equal to, or x minus a is equal to the derivative, or not the derivative. Well, yeah, the average derivative. So that would be f prime of x. But the thing is, this is accurate for the most part. However, also, I guess this is f of a, f prime of a. But you have to realize that the derivative formula only works as this bottom numerator goes to 0. In this case, we're using a linearization function, so if we pick a number that is too far from the original function, it can deviate. Now, this is not always the case because, for example, like a square root linearization function looks like this, and if you pick like a linearization right here, it uses like these. It's basically just a linear line, and if you estimate a point here, then you can see that it's pretty far. The differential, at least, or the residual, is pretty far from the actual y point on the curve. So if you use a point closer on the line like this, it becomes more and more accurate. So in this case, linearization only works when either the slope isn't changing too much. Like for example, right here, you can go here where the slope isn't changing so much, and linearization will be pretty accurate for a pretty long time actually, because it goes almost to a horizontal tangent. But here, as we can see, there is no bounds in the linearization function. The logic should be that x and a should be pretty close to each other in order for this thing to work, which is why in the Newton-Raphson method, which uses this linearization of sorts, you cannot use, there are certain cases where it doesn't work. Number one is where the function is erratic, like a sine wave. It's really hard to calculate the roots. I'm sure you can use some other algebraic methods to solve sine and cosine functions for their roots, but Newton-Raphson simply is inefficient for it. And even other functions, like even cubic functions, can be a little tricky with the Newton-Raphson method. So yeah. So what we've established is that this linearization function right here gives us a rough estimate of the point. And we say rough because the Newton-Raphson method isn't 100% foolproof unless it converges, which essentially means it goes to a point. There's a very high possibility. I mean, again, it's just an estimate, so it won't necessarily be at that point, or it won't be precisely at that point. So yeah, so that's why sometimes it's better to solve it algebraically, like with the quadratic formula. Why would you use linearization if you could just plug it into the quadratic formula, or if it's a linear function? I mean, why use linearization at all? So this essentially gives you the blueprint. But let's go over what the variables mean. So a would be your anchor point, and Newton, in the Newton method, many mathematicians and many textbooks change it to f of x of n, plus f prime x of n and x of n plus 1 minus x of n. So n plus 1 essentially is just your guess. So if n is your first guess, then 1 plus 1 is 2, so xn plus 1 will be your second guess. So the logic is pretty clear here. These are the anchor points. And when we say anchor, it's essentially the point where you find the derivative with. So that could be numerical or that can be algebraic. And algebraic is typically better since you could just plug the variables in, which is why you can just keep it in this form. So if you want to solve a root, we realize that this function is a rough estimate of the function. So it's essentially just the function in a different form, is how I like to think about it. So we can set it equal to 0. Well, let's use some algebra here. We'll subtract f of x of n divided by f prime of x of n plus x of n in order to get the second guess. So all that means is we plug in our first guess that makes this entire function 0, and that should give you your second guess, which should be even closer, and then you reiterate again and you try over and over in this loop and sequence so that the logic's clear. So again, since this is a rough estimate, x of n is essentially held constant because you're just choosing an anchor point on the function. And once you're choosing that anchor point, then you can start reiterating over the function. Let me actually go grab my book to grab an example. So I can do one. But, okay. Oh, this is my biology. I got it. Alright, so I can grab my book, so let's do an example here. So let's say we have a function f equals x cubed minus 2x minus 5. So also, something with this function, or with this thing, is that you can't choose an x value too far from where you think the x value is. So essentially this means that your guess has to be pretty accurate, or else it will not work very good, because choosing one that is too close or choosing one that is too far will essentially mean you have to reiterate over and over, and eventually it may lead to non-working, or not non-working, but non-convergent, a non-convergent series. So let's start with a guess that is essentially kind of accurate. So my book says to start with your starting functions, or starting point, to be 2. This is because if you plug in 2 here, you get 2 cubed, which is 8, minus 4, minus 5, which is negative 1, which is quite close to 0 in my opinion. Obviously, you can use delta epsilon to see how accurate that is. So the first step is we have to find the derivative. And the reason why we find the derivative, and I guess like we have to call it the function derivative because not a numerical derivative. You can also do a numerical derivative, but then you would have to recalculate it each time as opposed to just plugging it in. So everyone knows how to apply the power rule, so it's just going to be 3x squared minus 2. Simple as that. So now we just plug that into the formula that we have, which is f prime of x of n plus f prime of x of, x of n, x of n plus 1 minus x of n, which was the original. Actually, yeah, we already gave you the definition, so we're not going to do the logical stuff, or we're not going to do the proof again. So it's going to be x of n minus fx of n over the derivative at that point, which is kind of interesting because when I first saw the Newton-Raphson method, I was trying to figure out why the ratio of the function to its derivative will essentially reiterate the guess. So this is the original term, which is 2 that we're supposed to guess here. And this is kind of like the correction term that tells us to bring it back. So I don't know why the ratio of the function's output to its numerical derivative gives you that, but I guess it does. And in linear functions, actually, it would just be 1, or it would just be x plus the y-intercept divided by the numerical derivative at that point, or divided by the coefficient of mx, or m in this case. So this is what you have to do, and fortunately for us, they give us a pretty good guess. If I had to guess, I'll probably pick a little bit closer to like 1.8, but again, I guess they wanted to use an integer value. So we plug in the values that we know, 2 minus fx of n, which is just x cubed minus 2x minus 5, and then 3x squared minus 2. But since these are both functions of x of n, we can just write x of n right here. And doing the math, we get 2 minus, 2 plus 1 divided by 10, which is around 2.1. So essentially now we have a new x of n value that is slightly more accurate than the old one. And the reason being is because when we did that proof, the x value that makes it 0, we have to reiterate the thing. So that's kind of the logic behind it. And we do it over and over again. And your teacher should specify the number of iterations you do because, well, I don't know. Well, your teacher will probably give you that because, like, unless he wants it within like a specified precision interval, which is essentially how accurate it is to the actual root. But I don't think they will do that, and I think they'll just tell you, just do it like twice, and it'll be accurate enough. So let's do the second guess, which is going to be 2.1 minus the function again, divided by its numerical derivative, which is going to be 3x squared minus 2, and then just plug in the values. So 2.1 minus 2.1 cubed minus 2, 2.1 minus 5, 3, 2.1 squared minus 2. And like something I don't understand is like here it can get quite complicated. Like you would have to square 2.1 and stuff. Like for example, you would have to do 4.2 here. 2.1 squared is going to be 0.21 4.41, and then you would have to times it by 2.1 again. And like fortunately for like us, we have like some simple values like 2 plus 1/10 or 1/10. But it gets complicated when it's like 2.15 and stuff like that. And then you have to plug it into your calculator, which kind of makes me wonder because I guess like calculators and computers can actually just brute force it by just plugging in random values until x equals 0. But actually, computers use Newton-Raphson method in order to determine the thing. So if we do this and we compute the value, we get 2.0946. And if we plug this back into the original function, 2.096, we get some really close values. We get 0.061, which is really, really, really precise. So if you plug this into f of 0.061, or f of 11.2, or sorry, f of 2.0946, we get 0.061. Which is really, really accurate and precise. So somehow the genius mathematician Isaac Newton figured out a way to calculate how to solve roots. And that's essentially all that is, using linearization to understand new and old variables, using the old variable to iterate over and find a new numerical number to plug back into the function. And yeah, it all sounds like pretty hard to use, or pretty hard to understand. But once you understand how it was derived, which is through the linearization method, which was also used to calculate like square roots of like 99.5, then everything clicks and the logic is pretty sound. So that is the logic of this lesson.